Now, as we saw at the end of Chapter 4, when we were applying the Newton-Raphson method to a system of nonlinear equations, you recall there was an issue with approximating derivatives that came up with computing the partial derivatives associated with the Jacobian matrix. And that's where we're going to pick up here in Chapter 5 in terms of how we can approximate derivatives. Now, this gives us the opportunity to estimate derivatives without actually knowing analytically what the derivative is. So when you were taking derivatives and looking at differential calculus in your freshman courses, of course, you would learn, given a function, you would apply a formula and determine what the derivative was, and then you could evaluate it. So now what we're doing is we're estimating the derivative at a certain point numerically without having to look up a formula for the derivative. Because there may be in cases where it's too complicated to do that, or cases where the derivative doesn't, it's not available, or it's like I said, or it's not known perhaps. So given a function, as indicated here, y equals f of x, our goal is to determine the derivative at a particular point, let's say xk, x of k. And we're going to use forward and backward Taylor series expansions of the function. So Taylor series is just one of the most fundamental theories in numerical mathematics in terms of being able to represent the value of a function given previous or known values of the function. And so the very first formula we have here on the slide is a representation of forward movement in terms of estimating what the function is at x plus h if we know what the function is doing and several of its derivatives at x. So the idea here is that an estimate of the function at x plus h is given at with the value you have at f of x plus the rest of these terms. H is, of course, the distance that you're moving forward, and it's multiplied by the first derivative, h squared over 2 factorial times the second derivative, h cubed over 3 factorial times the third derivative, plus h to the fourth, and so on. So that's an infinite series. It doesn't continue. We can truncate it at any time, and then what we are leaving, the rest of it would constitute the error in the representation of the function. The next formula is going backwards. That's why it's called a backward Taylor series expansion, because having a value at f of x, we're estimating what f of x minus h. So we're going, instead of going to the right, we're going to the left. Pretty much everything stays the same, except you'll notice that this is an alternating series. In other words, the signs are alternating. You have f of x minus h prime of x plus h squared over 2 factorial f double prime of x, and then minus. So you'll notice that it's going to be negative on the odd derivatives there. And then you can, again, just replacing h with other values or functions of h, you could easily derive a rule for adding f of x plus 2h. You can see basically we're just substituting 2h wherever we had an h before. And similarly, down here at the bottom, you can take a farther stepward back, x minus 2h. So all of this is just based on the very first formula, which is just a representation of Taylor series a forward expansion. So these are ways that we can estimate, again, the function at another point, farther down on the x-axis, or to the left of the x-axis, or maybe x represents time, could be forward time or backwards in time, just depending upon what the application needs. Now, what's interesting is if you take combinations of those expansions, the forward and the backward, again, just so we understand the notation, if we were to take the forward expansion, which had this as the left-hand side, and then we took a corresponding backward expansion involving f of x minus h, and if you went back to the previous slide and you added those two expansions, the two right-hand sides together, this is what you would get. And what's interesting is you would get twice f of x, but all of the odd derivatives would go away because of those alternating signs. So that expansion there only has even derivatives. The same would be true for adding or subtracting 2h. So again, even order derivatives. And the second representation is just suppose you subtracted the two expansions. Take the forward one and then from it subtract the backward one. You would get this kind of an expansion, and notice all the even derivative terms would go away. So there's only odd derivatives involved. All right. So it may not clear out where we're headed, but again, we're trying to approximate a derivative, so we need to have the ability to represent the function changing through time, because remember, the derivative is the instantaneous rate of change of your function. The limit, as you remember, of f of x plus h minus f of x all over h. So we're just trying to use Taylor series so we can get a representation of what that movement must be like in the limit. And I want you to notice something very careful. I want you to pay attention to the second difference of the expansions. Look at this very carefully. And keep in mind we're trying to approximate a derivative. Well, there's the derivative term right there. So if you were to just pull that over to the left and pull everything over, you actually could get a representation of the derivative as f of prime of x. You'd have to divide by 2h, but you could get it as this f of x plus h minus f of x minus h all over 2h, and then you'd have those other remaining terms which could be represented as an error. It would be order h squared because you're going to divide through by 2h. This is key. What does this say? This shows you a way of approximating a derivative. If you're willing to advance a small step as well as go back a small step, see how the function has changed relative to this small step divided by 2h. That slope would sort of give you an estimate of what the derivative might be doing at x. And that leads us to the next slide then, because that is exactly what it's called the first central difference approximation for a derivative. In other words, you can approximate the first derivative using this formula where it takes two evaluations of the function and the truncation errors, if by just stopping there, that's going to be the error, and it behaves like h squared. So the error in using that as an approximation, you can see, is order of h squared. If h is too big, if very large, you've got a large error, and that's not going to be, this formula is not going to give you a very good estimate of the derivative. But as long as h is suitably small, so that you're just taking a little step forward and a little step backward, you can get a pretty good rough estimate of what the derivative is doing. So this is a very nice approach. This is what finite differences are like, and this is just some acronyms to we can use. First, central difference approximation. Central in the sense that it's centered about x. Definitely a difference approximation, and we're approximating the first derivative there. You can continue this strategy by looking at these other, going farther down those right-hand sides and taking and pulling out higher order derivatives, and you can actually come up with a finite difference representation for the second derivative, and here is its formula. What's different? Well, it takes three function evaluations. Error is still of order h squared. And here's the third derivative. Notice it takes four function evaluations. If you went to the fourth derivative, it takes 5. So it takes one more evaluation than the order of the derivative to approximate it. But notice all of the errors are order h squared for all of these approaches. So that leads us to, in the next slide, we can actually represent now all of these rules together by what's called a table of coefficients. This is Central Difference Approximation, CDA table of coefficients. It's a way of saying it's a very nice form that, a tabular lookup of how to approximate derivatives with this order h squared accuracy. The way this reads is that this would represent the left-hand side. So this would say, the first row would say that 2h times f prime of x is equal to what? Scan over, and these are the coefficients that go with those corresponding function evaluations. So this would be equal to f of x plus h, and then plus a net minus 1 times that would be the same thing as minus f of x minus h. So this is our first central difference approximation that we had before, meaning that if you're actually going to approximate the derivative, well, you understand that's an x there. I'm having a problem getting it. These selection things drive me crazy. So, or I'll just delete it and then just rewrite it. So this is 2h f prime of x, like that. And so if you just, if you're going to re-estimate the derivative, you'll just take this right-hand side and then divide it by 2h. Similarly, this next row tells you h squared times the second derivative at a point x should be estimated by a linear combination of 1 times f of x minus h minus 2 times f of x plus 1 times f of x plus h. And then if you're just isolating the second derivative, you'll divide all that by h squared. So this is a nice little table that, could easily be looked up. It could be programmed very easily. You could have a function that just simply pulls off the corresponding coefficients as necessary. And again, just keep in mind the first derivative needs 2 function evaluations, the second needs 3. It's the number of non-zeros you see in that row. Now, there are cases where you don't have the luxury of evaluating a function a step ahead plus h as well as x minus h. There could be boundary issues, approximating the derivative near a boundary, for example. So that leads us to another set of approximation formulas called the first non-central difference approximation. So keep in mind this word non-central. So you won't have something like f of x minus h and f of x plus h. So specifically, here's a representation of a non-centered difference approximation where you move a step ahead from where you were at f of x, divide by h, and then here are the rest of the terms that would be left over if you did that. And that's coming directly from Taylor's series. The big difference here is it still only takes 2 function evaluations like the centered difference, but the error is not as good. So what you're truncating acts like h, not h squared. So typically this won't be quite as accurate as the centered difference, but sometimes you don't have the ability to, again, evaluate f of x minus h. Similarly, you could have the first backward difference approximation. This is a first forward, this is backward because you were at f of x and you went backwards to f of x minus h. Again, the error term acts like O of h rather than h squared, so it's not as quite accurate. But this should make sense that it just depends on what data you have available. Can you given x, can you make an approximation in forward in time and have no problem, or can you use a value of x minus h backwards? So you're either using these two at the first 2 or the second 2, depending upon your application. But again, these are called the first forward difference approximations, FFDA, and the first backward difference approximations, FBDA. Just notation to help codify them. You can also have a forward difference approximation for the second derivative. Why is it forward? Because if you knew the function f of x, you would need to know it at x plus h and then f of x plus 2h. So you have to take another step forward. The error again, these forward difference or backward approximations are not as accurate as the central difference ones. So just remember that. And so now let's just look at the table of coefficients for the first forward difference and the first backward difference. Again, here's the first forward difference. How do you read this off? The first row would tell you that the formula would read h times f prime of x is equal to minus f of x plus 1 times f of x plus h. Or you easily could say that it's just f of x plus h, as we did before, minus f of x. And that would be equal to h times f prime of x. And so your approximation to the derivative would be just taking this left-hand side and dividing it through by h. And then you can see how the other higher-order derivative approximations work. Again, it's the same number of function evaluations as the center difference, but keep in mind the order of accuracy of these methods is O of h, not O of h squared. So that's the forward difference. Again, you're at x and you move forward. Notice you move either 1 step of h, 2 steps, 3 steps, or 4. And again, this just keeps going on for higher order derivatives. If you wanted 5th, 6th, 7th, 8th, 9th, 10 degree derivatives, order derivatives, this table would just keep getting larger and larger. Backward, it's very similar. Coefficients are a little bit different. They're not exactly the same, and they're not quite transposed either. But again, if you had f of x, you would need to go back 1 step, 2 steps, 3 steps, and 4 steps. And here's how the rules would work in terms of reading off the coefficients times their corresponding function evaluation. Again, in software, you would code up all these tables, and then depending upon, the user can approximate any number of derivatives that you're going to provide, depending upon how large the table is. So a question arises, well, the central difference formulas seem great in terms of O of h squared, but again, maybe some applications you're not going to have the ability to move forward and backward to approximate the derivative at x. So how could you produce a non-central difference formula that had the better truncation errors? In other words, where the error act like O of h squared rather than O of h. Because keep in mind, for small h, that will be a much smaller value. H squared will be much smaller than h when you're less than 1. So, well, it can be done. Doing a little algebraic combinations with our Taylor series, you can actually come up with what's called the second forward difference approximation. The other ones are called first order, the first forward difference and had O of h squared. The second forward difference approximations are order h squared. So these are higher accurate. But here's the big difference. Remember, if you go back to the previous tables, you'll notice that the forward and backward difference only used, for example, for the first derivative, 2 function evaluations. This one's using 3. So it takes 3 function evaluations to get this order accuracy. Now, if you contrast that with the central difference formula for f prime of x, it only needed 2. So here's the price you're going to pay. To be able to move completely forward, it's going to cost you 1 more function evaluation to get that kind of accuracy, comparable to the center difference. So here they are. Here's the table then for the second forward finite difference approximations. Again, these are a little bit, this table is denser because it's going to take 3 function evaluations for the first derivative, 4 for the second, 5 for the third derivative, and you can see clearly here it's going to take 6 for the fourth derivative. It takes 2 more function evaluations than the order of the derivative. And these values do get a little bit larger. These coefficients are exceedingly more larger than they were. But nevertheless, this is a way, if you're unable to move backwards, or this is on a boundary, if the x was lying on a boundary for some reason and you could only move forward, this would be a way of evaluating that derivative moving different steps h along the x-axis or through time if x represents time. I'm not going to show the table for a second backward finite difference approximation to get order of h squared, but it's on page 187 in the textbook, very, very similar to the one we just did for the second forward finite difference approximation. One thing you're going to notice is that the sums of the coefficients in all these tables, if you traverse any row, they always sum up to 0. So that's a good way of sort of checking to make sure there's no errors in your table, especially if you're programming it. So all the values across the row would sum to 0. And of course, when h is taken to be very, very small, you have to be careful that when h is very, very tiny, f of x and f of x plus h are not very different. Same thing with plus or minus 2h and so forth. So the values can get so close that subtraction could produce a loss of figures. So you don't want h to be exceedingly small, but at the same time, of course, if it's too large, the error in using the finite difference approximation is just going to be too large to tolerate. So we're going to stop this lecture at here. The next lecture we'll pick up with some examples of applying these difference approximations and then talk about a technique called Richardson extrapolation that can boost the accuracy of these approximations for the derivatives even more.